right?
Yes, ma'am.
Okay. So let's start today's class, and I hope people will join soon. So in the last class, we were discussing about how to find out. So if you have, if a system is given to you in the form of a state space equations, so then from the state space equations or from the state equations, how you can find out how the transient response of the system will look like. So we were looking at how to solve, or rather how to obtain the solution for state equations. Okay, so just to revise a little bit, so the system transient response, it can be obtained by solving the state equations. Now if you have an unforced system means which does not have any input to it. Okay, so thus the response of the system is only occurring due to the initial conditions which are present in the system. Okay, so that kind of a system, the state equation will be given by x dot t is equal to a of xt. So that the b ut terms is equals to 0. So that plus b ut will become equal to 0, and the state equation will be x dot equals to ax. And the initial condition is given as x at time t equals to 0 is x0. So if you have a system which looks something like this, or the representation of the system is in this form, and this is a system where there is no input present. So that means it's an unforced system. Okay. So for that kind of a system, the solution was, so we had already derived how to come to this solution. So the solution looked like that the value of xt would be equals to e to the power at multiplied by x0, where a is the system matrix that you have, x is the state variables that you have considered, and x0 is obviously the initial condition or the initial state of the system. Okay, so now this term, this e to the power at, this term is basically known as the matrix polynomial, or you can say that this can also be known as something which is known as state transition matrix. Okay, and this e to the power at, that can be expanded in a form like this, where you can write e to the power at will be equals to an identity matrix I plus a multiplied by t, then 1 by 2 factorial a square t square, and so on and so forth. Okay, so from here you can say that, so from this solution you can say that if the initial condition of this or the initial state of the system is x0, so after time t, the state of the equation, state of the system goes to something which is given by xt. Okay, so that means you can say that the initial state, that is x0 at t equals to 0, that is driven to a different state xt at time t. Okay, so this transition that is happening in the state, that is from the initial state to a different state, this transition is basically being carried out by this function which is known as e to the power at. Okay, so that's why this is known as this is called a state transition matrix, and this is also denoted by this by matrix exponential also. So these are like synonymous terms. You can say that e to the power at is known as state transition matrix. The state transition matrix is basically the most common term. Mostly this term is only generally used for defining the value of e to the power at, and you can also write e to the power at. It can be denoted by phi of t. So you can say that phi t is basically the state transition matrix, that is STM, or otherwise it is known as a matrix polynomial. Okay, so this was the case where your system input, there was no input to your system. Okay, so now we'll see that when we have a system which is an forced system. A forced system means the value of ut, the input to the system, will no longer be equals to 0. There will be a finite value of the input. The input can be in different form. It can be a step input, it can be a ramp input, depending on your system. Okay, so that means, so now if you write the state equations for a forced system, that is the non-homogeneous state equation of a forced system, it will be given by the standard equation x dot is equals to ax plus bu, and the initial condition is at x at t time t equals to 0 is equals to x0. Okay, so from here you can rearrange this equation and you can write that x dot t minus, you take this term to the left side, so x dot t minus a of xt is equals to b into ut, right? So next, what if we multiply both the sides with e to the power minus at, so you can write that e to the power minus at multiplied by x dot minus ax will be equals to, on the right hand side you will have e to the power minus at into bu. Okay, and this term, this e to the power minus at multiplied by x dot t minus e to the power minus at multiplied by a of xt. This is nothing but, if you take, so let's take the, if you take the derivative of e to the power minus at of xt, this you can write, in the first case you will have e to the power minus at, you will have x dot t, then minus you will have xt multiplied by e to the power at, and this minus, sorry, it will be minus e to the power at, right? So you can see that this is nothing but the equation on the left hand side. So you can say that this term can be replaced by the d dt of e to the power minus at into xt, right? So you can, from this equation what you can do is that we can take the, if you take the integral from t equals, from time t equals to 0 to time t equals to t of both sides, so you will have on the left hand side you will have integral of d dt of this term e to the power minus at into xt dt, and on the right hand side you will have integral 0 to t e to the power minus a tau b u tau d tau. Okay, and this term on the left, so you have an integral, and then inside the integral you have a derivative, so that means these two gets sort of cancelled out and you are left with e to the power minus at into xt from time the limits being 0 and t. Okay, so you just simply substitute the limits, so you will have e to the power minus at into x minus x0 will be equals to integral 0 to t e to the power minus a tau into b u tau d tau, right? So, and from this equation you can simply rewrite to find what will be the value of xt, because xt is ultimately the solution for this equation, right? So you can write that xt will be equals to this e to the power at, you will have to divide the whole thing with e to the power minus at, so you will have e to the power at multiplied by x0 plus integral of 0 to t, this e to the power minus at will go inside the integral, you will end up with e to the power a t minus tau b u tau d tau, right? So here you can see that this part of the solution, this is the homogeneous solution. Homogeneous solution means the solution or the component of the overall expression which is present only due to the initial conditions. So that means the effect, when the effect of the input is equals to 0, if the input to the system is equals to 0, then whatever the output of the system will be, that is the homogeneous solution, which is what we saw in the last case when we were talking about an unforced system. Okay, and because of, and the component of the overall solution which is responsible or which is dependent on the input of the system, that would be this part. This part is known as the forced solution of the system. So overall you can say that if you have a system whose state equation is given by this, and if you know the value of the input to the system, then the state matrix, then this matrix B, if you know all these values, then you can simply find out what would be the output or what would be the transient response of the system. Okay, so in this equation you see that we have considered that the initial time t is equals to 0. Okay, so for that's why we have written that x0. So x0 is basically x at t equals to 0 is equals to x0, right? So now if you consider the initial state at t equals to t0, what we'll do is that we'll simply have to substitute that minus t0 inside all these terms. So you will have e to the power at will become e to the power at minus t0. This x0 will become x at t0. Then you will have, instead of 0, the lower limit of the integral will be t0 inside, and the and these terms will remain the same. So this you can say is a more general or a more generic form of the solution for the equation. So, and this one is a specialized case where the value of T0 is equals to 0. For this solution, the value of T0 is equals to 0. So if you just simply put T0 equals to 0, you will end up with this equation. So you can say that the general form of the solution of the state equation, which looks like this, x dot is equals to ax plus bu, that is given by this expression. And this is nothing but the transient response of the system to a particular input. So this is the input to your system. So depending on whether your input is a step input or a ramp input or a parabolic input, depending on that, the value of ut or u tau will change, and accordingly you can find out what will be the overall transient response for your system. Okay. So now, so as we have already defined that the state transition matrix is known as phi t, and phi t is equals to e to the power at, where a is the system matrix. Okay, and here we are considering when we are writing that the state transition matrix is equals to e to the power at, that time we are considering that the initial time or the initial state of the system is occurring at t equals to 0. Okay, and in general, for if you write the general expression, then you can say that for a linear time invariant system, if the initial time is t equals to t0, so that means the initial state of the system is defined by x at t0. So this would be the initial state of the system. Then we can say that the state transition matrix will be defined by phi at t minus t0, and that would be equals to e to the power a t minus t0. Okay, so now let's talk about some properties of the state transition matrix. So these properties would be useful when we try to solve the when we try to find out the state the transient response of a given system for different kinds of input. Okay, so as you can see that if you want to find the value of phi 0 is equals to nothing but e to the power a0, so that means it would be an identity matrix I. Okay, so similarly, if you write phi t, so phi t is equals to e to the power at, you can simply write e to the power minus at, the whole thing to the power minus 1. So e to the power minus at is nothing but phi of minus t, right? So this term becomes equals to phi of minus t inverse, or in other terms you can write that phi of minus t is equals to phi inverse of t. Okay, so this is another property of the state transition matrix. Similarly, if you write phi t of t1 plus t2, that would be equals to e to the power a t1 plus t2. This can be simplified or this can be expanded as e to the power a t1 multiplied by e to the power a t2. This is nothing but phi t1. This is phi t2. So you have multiplication of phi t1 multiplied by phi t2, or vice versa, phi t2 multiplied by phi t1. So overall you can say that phi at time t1 plus t2 would be equals to some product of phi at time t2 multiplied by the value of the state transition matrix at time t1. Okay. Now similarly, if you write the expression for the solution for the state equation, that is xt, you can write xt is equals to phi t. So here we have seen that xt is equals to e to the power at. So e to the power at we will substitute by phi t. Then we'll have x0 plus integral 0 to t. You can write that this term e to the power at minus tau would be equals to phi t minus tau, and then you will have this term, right? So that is given over here. So you have phi t, and then you have x0. Then you have inside the integral you have phi t minus tau, because we had e to the power at minus tau, which is nothing but phi of t minus tau, and then you have b u tau d tau. So this would be the equation for the solution for a given system, provided that the initial state is considered at t equals to 0, and this state is known, provided that you know the value of this x0. Okay, so now if the initial state is not at t equals to 0 but at some other time t equals to t0, then you can simply just generalize this previous equation and you can write it as xt is equals to phi t minus t0 x at t0 plus integral T0 to T, phi T minus tau, B into U tau D tau. Okay, so these are some of the important or some of the properties of the state transition matrix which would be generally useful when we are solving for different equations or when we are trying to find out the transient response for a given system. Okay, so now the state transition matrix, basically the value of the state transition matrix, as we know that this is equals to e to the power at, right? So now if you know the matrix A, then computing the value of e to the power at is becoming will become a little tedious. So what we can do is that we can find the value of the state transition matrix by different other methods also. Okay, so there are two methods. So one is by we can compute the value of the state transition matrix by using Laplace transform. Okay, so first let's take the case where we have an unforced system. Okay, so the state equation for that unforced system will be equals to x dot is equals to ax. This is unforced system, means that the value of ut is equals to 0, right? So that means the general equation that we have, so this is the general state equation. So this term will be equals to 0 since it is an unforced system. So this term becomes equals to 0. So you have x dot is equals to ax. And the initial state is given as x0 is equals to x at time t equals to 0. 0 is equals to x0. Okay. And A is a constant matrix which is given. Okay. So then if you take the Laplace transform of this equation, so you will end up with, you will have x into capital X minus x0 will be equals to a into capital X, xs, right? So you can rearrange this equation and you can take this axs to the left hand side, x0 to the right hand side, and you can see that it will become s into I minus a multiplied by xs will be equals to x0, right? So xs would be equals to this matrix si minus a, inverse of that matrix multiplied by x0, right? And so this is the Laplace transform form. So if you take the inverse Laplace of this equation, you will get the value of xt. Okay, so xt would be Laplace inverse of this whole thing. This term is constant. This x0 is basically constant and it is known to us. So x0 will be outside, and you can write that xt is equals to Laplace inverse of this Laplace inverse of si minus a, this matrix inverse. Okay. So you can say that xt is basically the unforced response of the system. And previously we had seen that for an unforced system, the solution for the state equation was expressed by something like this: xt is equals to e to the power at into x0, where x0 is equals to, so this x0 is equals to x0, which is already given. So you can compare these two equations. So you can compare, if you say this is equation number 1 and this whole thing is, let's say, equation number 2. So if you compare these two equations, you can see that this term, this Laplace inverse of si minus a, this matrix inverse, that is nothing but e to the power at. So you can write that by comparing these two equations, the state transition matrix, that is phi t, which is nothing but, which is same as e to the power at, that will be equals to Laplace inverse of this matrix si minus a inverse. Okay, or similarly you can substitute this si minus a to the power inverse this matrix by phi of s, where you can write that phi of s is called the resolvent matrix. Okay, this we had seen earlier also, that phi of s was called resolvent matrix. So you can say that the state transition matrix can be obtained by taking the Laplace inverse of this matrix si minus a inverse. So a is known to you. Whenever you have the system is given to you, you can express the system in form of the state space equation. So the moment you express the system in form of a state space equation, so you will know what will be the value of this a. So a is known to you, so you can find what would be the inverse of this matrix si minus a. Once you find the inverse of this matrix, you can simply take the Laplace inverse of that resolvent matrix and you will end up with the value of the state transition matrix. Okay. Similarly, so this was the case for when you had an unforced system. So unforced system means when the value of input to your system was equals to 0. Okay. So now if you have a forced system, so forced system means the state equation will be given as x dot is equals to ax plus bu, and the initial condition is given like this. Similarly, we take the Laplace transform of this equation, and you will have x of xs minus x0 will be equals to a of xs plus b into us, right? So similarly, you rearrange this equation, you will end up with si minus a multiplied by xs will be equals to x0 plus b into us, right? And if you write the if you simply write the expression for xs, so xs will be equals to si minus a inverse multiplied by x0 plus si minus a inverse multiplied by b multiplied by us. Okay. Then again you take the inverse Laplace transform, and you will have xt will be equals to in Laplace inverse of this term si minus a inverse multiplied by x0 plus Laplace inverse of this whole term, this si minus a inverse b into us, right? And you can write and you can compare this, or in the previous case we had seen that this value of phi t is nothing but Laplace inverse of si minus a inverse, right? So you can simply substitute this by the state transition matrix phi t. So xt will be equals to phi t into x0 plus Laplace inverse of this thing is nothing but phi s. So this will be Laplace inverse of phi s into b into us, right? And this xt is basically known as the forced response of the system. Forced response of the system means whenever your system is getting excited or the input to your system is a finite input, in that case how the system would respond, that in the time domain, that is known as the forced response of your system. So you can find what would be the forced response of your system if you can simply compute the value of this phi t. Okay, and the value of the phi t, it can be computed from this equation which is given. Phi t is equals to Laplace inverse of si minus a inverse, right? So this is one way of this is one method of computing or computation of the state transition matrix. Okay, so this method is well enough, or this is quite simple enough if we were dealing with a what do you say, if you are dealing with a very small system, or if you are dealing with a system which is of lower order. Okay, but in case if you have a system which is of a very high order, that in case that this matrix A becomes very high, so usually we are dealing with maximum a matrix of like 2 cross 2 or 3 cross 3, that kind of a matrix. In case if you have a larger system, then this matrix, the dimension of this matrix will become higher. Okay, so A will become maybe n cross n matrix, it might be 9 cross 9 matrix. Okay, so in those kind of a system, this, if you want to compute the state transition matrix using this Laplace transform method, that becomes much more tedious. So in those kind of a system, what we do is that we use something else which is known as a Cayley-Hamilton method. We use that kind of a method in order to find out what would be the, or in order to compute the value of the state transition matrix. Okay, so before I move on to the Cayley-Hamilton method, so now let's try to solve a problem. So in this problem, what is given is that you have to find out what would be the unit step response for the system whose state equation is given by this. Okay, so this is the state equation. So that means this is your matrix A, this is your matrix B, and this is the input which is provided. So X transpose is provided. So that means you can write that X0 will be equals to 1, 0, right? So the first step is that we have, so in order to find out the unit step response, we need to find out that state transition matrix. So once we know the state transition matrix, we can simply put this, we can simply obtain this response to the system by substituting the state transition matrix over here in this equation. Okay, so for that what we do is that, so this phi, the value of phi s is equals to si minus a inverse. So we have to compute the value of this si minus a. So si is not, so if you write si would be equals to s0, 0, s. Okay, so si minus a, so this is a, will be this matrix s minus 1, 0, minus 1 and s minus 1. Okay, so if you find the determinant of this matrix, so determinant of this matrix is equals to s minus 1 whole square, right? So then and you know that for finding the inverse of a matrix, what you need is that in the numerator you will have the adjoint of the matrix divided by the determinant of the corresponding matrix. Okay, so if you find out, sorry. Someone's mic is Kumar. Okay. So please don't unmute your mic in case you're doing something else. Okay. So in case you have, so that means that you can find the, so if you, once you have computed the value of Si minus A, so you can find out what would be the inverse matrix, right? So Si minus A inverse will be a matrix this, and this is nothing but the resolvent matrix phi of S. Okay, so from phi, if you know phi of S, so you can find phi t just by simply taking the Laplace inverse of this matrix. Okay, so taking Laplace inverse means, so you will have to take the inverse Laplace of each and individual elements of this matrix. So the first element would be the Laplace inverse of 1 by S minus 1. This element will be Laplace inverse of 1 by S minus 1 whole square. This would obviously be 0, and this one would be again Laplace inverse of 1 by S minus 1. Okay. So if you take the Laplace inverses, so this term will be e to the power t, this term becomes t e to the power t, and similarly e to the power t. So you have found out, you can compute what would be the value of phi t. Okay, and in this equation you see that if you know the value of phi t, you know the value of phi s, b is also known to you, u is also known to you. So if you, so all that, and x0 is also given. Okay, so that means you know all the terms on the right hand side. You just have to compute the individual terms and add them up in order to find out what would be the final solution of the equation of the system. Okay, so similarly, so you can write this equation. So this was the solution. So xt was equals to e to the power at x0, or in other terms you can write a plus integral 0 to t e to the power a t minus tau b into u tau t tau. So this is just the expression which we had derived. So in this equation you can write e to the power a t will be here. This e to the power a t minus tau will be equals to phi of minus tau, right? Because we are considering at t equals to T0 is equals to 0. Okay, so here you will have phi of minus tau, b of u tau. So phi of minus tau you can find, you already know phi of t. So that means phi of minus tau would be equals to, you just substitute the value of t with minus tau. So this would be the expression for phi of minus tau. B is also known to you, and u tau is equals to 1 because it is given that the input to your system is a unit step input. So u tau is equals to 1. So you can compute this term which is inside. So that means this would be equals to phi of minus tau, b of u tau would be equals to just the product of these two matrices, which is nothing but this. Okay, and so this term is known to you, which is given by this expression. Okay, so now what you have to do is that you have to simply take the integral of these two terms so that you can compute this whole this term. So you will have integral 0 to t phi of minus tau b into u tau d tau. Take the integrals for the individual terms, and this is the final expression. Okay, so e to the power at is already known to you. E to the power at is nothing but phi of t. Okay, so you have phi t multiplied by x0 plus integral 0 to t phi of minus tau b of u tau d tau. This is also known to you. This also you have already computed. So now what you have to do is that you have to simply substitute all these values and then do the multiplication or addition, subtraction, whatever is given. So you have to add these two matrices and then multiply that one with this matrix, and you will end up with the solution for the equation, solution for the given system. So that means this xt, that is the unit step input for your system, that xt will be given by 2 e to the is given in this matrix form. This is 2 e to the power minus t minus 1, and the second term is 2t e to the power minus t. So this is the this you can say that this is the unit step response for the system which is given to you. So this was the system which was given to you with the initial condition this. So you could find out what would be the unit step response. Similarly, if you had unit ramp response, so in that case the value of u tau would not be equals to 1. So in case if you had unit ramp response, so it would have been u tau would be equals to 1 by t, or ut will be equals to t or tau. Then similarly you have to put the value of tau over here and continue with the calculation. Okay, so it's like that the first step is always to find out the resolvent matrix. From the resolvent matrix, you find out the state transition matrix, and once you have known the state transition matrix and the resolvent matrix, you can simply put those values into the given equation, the given form of the equation. You can simply substitute these values, and you will end up with the step response or any forced response of the system. So now next we'll see that how to compute the state transition matrix using the Cayley-Hamilton theorem. Okay, so as I've already told that if you have a larger system where the matrix where the system matrix A is quite large, in those kind of a system it is difficult to compute the state transition matrix using the Laplace transform method. Okay, so for that we will be using this Cayley-Hamilton theorem. Okay, so this Cayley-Hamilton theorem basically it states that if you have a square matrix, so every square matrix A, it satisfies its own characteristic equation. So what does it mean? So if you have a matrix A, so then you can write that the characteristic equation for that matrix is given by Q of lambda is equals to determinant of lambda I minus A equal to 0, right? This you can simply you can expand in this form, lambda to the power n plus A1 lambda to the power n minus 1 till An will be equals to 0. Okay, so Cayley-Hamilton theorem states that every square matrix A would satisfy its own characteristic equation. So you can simply substitute the value of A in place of lambda. So you can write that QA will be equals to also 0. So QA will be equals to, you substitute lambda with A, so you will end up with A to the power n plus A1 A to the power n minus 1 till the last term An multiplied by identity matrix I will be equals to 0. Okay, so this is the theorem of Cayley-Hamilton method. Okay, so we'll not go into the proof of how this is coming. So this is, you just remember that this is what the theorem states. Okay, so and this theorem will be, it actually provides a very simple procedure for when we are trying to evaluate the state transition matrix for a larger system. Okay, so now if you have this matrix, you can find out what would be the eigenvalues of that matrix. Okay, so once you find out the eigenvalues of this matrix A, so let us say that these eigenvalues are lambda 1, lambda 2 till lambda n. Okay, so you can simply write that the matrix polynomial or the state transition matrix f of A would be equals to k0 into I plus k1 into A plus k1 into A square and so on and so forth. Okay, so you can, and if you take so this is in matrix form because all these terms A square, these are all in matrix form. If you write the corresponding scalar polynomial, in case of scalar polynomial, this matrix A will be simply substituted by a scalar quantity lambda. So you can write f of lambda will be equals to k0 plus k1 lambda plus k1 lambda square and so on and so forth. Now, if you have this, so this expression f of lambda, so now if you divide this matrix polynomial or this f lambda by the characteristic equation q lambda, so let's say that f lambda by q lambda is some matrix capital Q of lambda plus something like this r lambda by q lambda. Okay, so and where r lambda is basically the remainder polynomial form. Okay, so you can write that f lambda will be equals to this capital Q lambda multiplied by small q lambda plus r lambda. right? Now we have already known that if we are so, and this the value of this r lambda, so r lambda is the remainder polynomial, and it can be expressed in this form. So alpha 0 plus alpha 1 into lambda plus alpha 2 lambda square till alpha n minus 1 lambda to the power n minus 1. So that means you can say that you can evaluate the state transition matrix, which is given by f lambda or fa. So you can evaluate the state transition matrix for different values of lambda. Okay, so now if we find out the values of f lambda at the eigenvalues lambda 1, lambda 2 till lambda n, so then we can write that this term will be equals to 0 because q lambda is equals to 0. Right, because since we have a matrix A and the eigenvalues of the matrix are lambda 1, lambda 2 till so on and so forth, and the eigenvalues are found. So this is the characteristic equation. So the solution of the characteristic equation will give you the eigenvalues of that matrix. Okay, so that means that q of lambda 1 is equals to 0, q of lambda 2 is equals to 0, and similarly you can write that q of lambda is equals to 0. So this term will become equals to 0. So f lambda will be equals to r of lambda, provided that the lambda values are the eigenvalues of this matrix A. So you can write f of lambda I is equals to r of lambda I. Okay, so now so that means if you have, like, let's say you have n number of eigenvalues, so you can find out n number of equations, n number of the equations can be found out, right? And from the n number of equations, what you can do is that you can simply find out what will be the values of, you can solve those n number of equations and you can find out the values of these coefficients, this alpha 0, alpha 1 till alpha n minus 1. Okay, so once you have found out those equations, then you can simply write that this f of lambda will be given by this alpha 0 plus alpha 1 into lambda and with this equation. Okay, so similarly if you substitute the value, so in case of, instead of using this lambda I, if you substitute this A, the matrix A, so you can write from this equation f of A will be equals to q of A multiplied by small q of A plus r into r of A, which is given by this. Similarly, and the Cayley-Hamilton theorem says that so if you have a square matrix Q, so that means that a square matrix A, so that means that square matrix will be will satisfy its own characteristic equation. So that means the value of QA will be equals to 0. Similarly, so if QA is equals to 0, this term goes to 0. So you will end up with FA will be equals to RA. Right, and RA you can express from this equation. So alpha 0 into I plus alpha 1 into A, and so on and so forth. So if you can find out the values of this alpha 0, alpha 1, so you find out the values of the eigenvalues, and you can find out what, and you will have n number of simultaneous equations. You have to solve the n number of simultaneous equations and you can find out these constant coefficients. And once you have found out that, you can simply calculate what would be the value of this FA, which is nothing but so FA is basically the state transition matrix. Okay. So just to summarize the steps which you need to follow in order to evaluate the matrix polynomial or the state transition matrix using this Cayley-Hamilton theorem is that first of all you have to find the eigenvalues of the matrix A. Okay, so now if you have like all the eigenvalues are distinct, so that means none of the eigenvalues have the same value, so then you will have n simultaneous equations and you can solve these n simultaneous equations which you find from this equation f of lambda I is equals to r of lambda I. So by solving those n equations, you can find out this n from alpha 0 to alpha n minus 1, these coefficients. Okay, so once you can find out these coefficients, you can simply find what would be the value of the state transition matrix from this equation. You can substitute the values of alpha 0, alpha 1, a square, all these terms, and you can find out the value of the state transition matrix. Okay, so now what would happen if the eigenvalues are not distinct? Okay, so let's say if you have like out of 9 eigenvalues, 3 of the eigenvalues are of the same value. Okay, so that means you will no longer have n simultaneous equations. So you will no longer have 9 different simultaneous equations. You will have only So let's say if you have 9 out of 9 eigenvalues, 3 have the same values. 3 have same value. So if you have it has a eigenvalue lambda k, which is of the order m, which is m is equals to 3 in this case, then you will have, for corresponding to this m number of eigenvalues, you will only have one independent equation by substituting this value of lambda k in the equation f lambda is equals to r lambda, right? So that means overall you will end up with you will have m minus 1 number of linear equations, so that m minus 1 number of linear equations can be obtained by differentiating the given equation. So the given equation was this. So this term is obviously is equals to 0, this term, because q lambda is equals to 0. So what you can do is that you can write f lambda is equals to r lambda. You can take the derivative of both the sides. Okay. So if there are so this value of j, if you vary the value of j from 0 to m minus 1, so you take the derivative of both the sides at lambda is equals to lambda k, and you, from this equation, if you equate the value, then you will get the other m minus 1 equations, and so overall you will have total n number of simultaneous equations, and similarly you can solve them in order to find out the values of alpha 0, alpha 1 and these coefficients. Okay, so now let's try to solve an example, then I think it would be more clear how to compute this state transition matrix using this Cayley-Hamilton method. Okay, so let us say that it is given that this state transition matrix FA is equals to a to the power 10. Okay, and you have the matrix A is given by A equals to this matrix, right? So now if you want to compute the value of this state transition matrix by simply multiplying this matrix A 10 times, then obviously you can understand that it would be a very tedious process. Okay, so for that what we would do is that we would use this Cayley-Hamilton method. So the first step was that you have to find out the eigenvalues of this matrix A. Okay, so in order to find out that eigenvalues, what you have to write is that you have to write the characteristic equation. So the characteristic equation of this matrix A will be given by lambda I minus A is equals to 0, right? So from this one you can write that lambda I minus A will be this matrix lambda minus 1 to lambda plus 3, this. So basically the determinant of this matrix will be equals to 0. Okay, so this one basically becomes lambda into lambda plus 3 plus 2 is equals to 0, and if you solve this equation you will get lambda plus 1 into lambda plus 2 is equals to 0. So that means there are two eigenvalues, one is lambda 1, another one is lambda 2, which is equals to minus 2. So you have two distinct eigenvalues of the matrix A. Okay, so now what you will do is that, so that means we can use so we will have two simultaneous equations and we can find out the value of alpha 0 and alpha 1. So since A, the order of this matrix is 2, so you can write that the value of r lambda will be equals to alpha 0 plus alpha 1 into A. The higher order terms will not be there because this is a second order equation. Okay, so from here what you can do is that you can, and this would be nothing but f of lambda, right? So you can find out the value of f of lambda 1. So f of lambda 1 would be alpha 0 plus alpha, so this will not be equals to A, this would be lambda. So this would be alpha 1 into lambda 1. So this is equals to alpha 0 minus alpha 1, and f of lambda 2 will be equals to alpha 0 plus alpha 1 lambda 2, right? So this would be equals to alpha 0 minus 2 alpha 1, right? And it is given that the value of FA is equals to a to the power 10. So you can write that this one will be equals to a to the power 10. So A is lambda 1. So lambda 1 to the power 10. Similarly, this would be equals to lambda 2 whole to the power 10, right? So lambda 1, so you have two equations. So the first equation is alpha 0 minus alpha 1 is equals to minus 1 to the power 10, and the second equation is alpha 0 minus 2 alpha 1 is equals to minus 2 to the power 10. Right? So you can simply solve these two equations and you can find out the values of alpha 0. So alpha 0, I am just writing the final answers. So alpha 0 is minus 1022 and alpha 1 is equals to minus 1023. Okay. So once you have found out the value of alpha 0 and alpha 1, you can simply find out what would be the value of Fa. So Fa would be nothing but alpha 0 into I plus alpha 1 into A, right? So you can simply write alpha 0, so minus 1022 into the identity matrix I minus 1023 into the matrix A, right? So you can simply substitute these two values and you do the addition and you will end up with the state transition matrix, and this, the values would be, this is minus 1022 minus 1023, then you have 2046 over here and 2047 over here. So this is basically the state transition matrix for this system. So Fa will be given by this equation. So the steps are, first of all, find out what would be the eigenvalues of your equation of the matrix. Then from the eigenvalues you find out what are the you find the n number of simultaneous equations, you solve them, you find these coefficients alpha 0, alpha 1 till alpha n minus 1, and from that you can simply substitute the values. So Fa is equals to alpha 0 1 into I plus alpha 1 A plus alpha 2 A to A square and so on and so forth. You can simply substitute those values and you will end up with the state transition matrix. Similarly, if you, let's take another example. So let's say that in this case, if you have, in this case, this Fa is given by e to the power at. Okay, so in this case also, so the first thing is like you will write the characteristic equation. So the characteristic equation is q lambda is equals to lambda I minus A is equals to 0, right? So you can, so lambda I minus A is equals to, you can write that this will be lambda minus 1 lambda plus 2 is equals to 0. So from here you can write lambda multiplied by lambda plus 2 plus 1 is equals to 0, and if you solve, so you will see this is lambda plus 1 whole square. So here you see that there are two eigenvalues, but these two eigenvalues are not distinct, like, right? So that means both the eigenvalues have the same magnitude. So since both the values have the same magnitude, so that means we will not have two different simultaneous equations from the, so this R lambda was equals to alpha 0 plus alpha 1 into lambda, right? Now since the value of lambda 1 and lambda 2 are same, so that means both the simultaneous equations which you will find from by substituting the value of lambda 1 and lambda 2 will be same. Okay, so what we would need to do is that we have to find out. So the first one you can write. So f of minus 1 is equals to alpha 0 minus alpha 1, which is equals to f is given as e to the power at. So that means this would be e to the power minus t. So this is your one equation that you have. So for finding the second equation, what we have to do is that we have to take the derivative. Okay. So we know that f of lambda is equals to r of lambda, right? So what we'll do is that we'll simply take the derivative with respect to lambda. So f of lambda at this value, lambda 1 is equals to minus 1. So this would be equals to nothing but d of t lambda of r lambda at lambda equals to minus 1, right? So if you take the derivative of r of lambda, so this will be equals to nothing but alpha 1. So you will have, so this term will be equals to alpha 1, and from the left hand side you have e to the power at. So f of lambda is equals to e to the power lambda t. So that means d dt of f of lambda is equals to lambda is equals, so d dt of f of minus 1 is equals to ddt of e to the power minus t, which is nothing but t e to the power minus t. So you can write that lambda alpha 1 will be equals to t e to the power minus t. So now you will have two equations. This is equation number 1 and this is equation number 2. You solve these two equations and you can find out the value of alpha 0 and alpha 1. So you can write that alpha 1, obviously the value is given. Alpha 1 is equals to t e to the power minus t. So alpha 0 would be equals to t plus 1 e to the power minus t. Okay, so once you have known the value of alpha 0 and alpha 1, you can find out the value of, let me write it over here. So f of a would be equals to alpha 0 into I plus alpha 1 into a, right? So alpha 1 you already know, alpha 0 is already known to you, alpha 1 is known to you, I identity matrix you know, this A matrix also you know. So you simply substitute the values and you will find out the value of f of a. So f of a, basically the value of f of a will look something like this: t plus 1 e to the power minus t e to the power this. So this would be the state transition matrix for this system which is provided to you. Okay, so that means that using this Cayley-Hamilton method, you can find out the value of the state transition matrix for a given system, which is provided that the not only provided, but given that if your system is a large system, then computing the state transition matrix using this Cayley-Hamilton method becomes much more easier. For a smaller system, for a like first order or a second order system, then in that case you can simply use the Laplace transform method also, where you can find out the value of this state transition matrix just by simply taking the Laplace inverse of this Si minus A, this inverse of this matrix. This method can also be used for finding out the value of this state transition matrix, but in general it is easier to find the state transition matrix using the Cayley-Hamilton method, because that gives that is sort of, you can say that from the computation point of view, that is slightly easier compared to the Laplace transform method when you're dealing with a higher or a larger order system. Okay, so do you have so I'll stop here today. So do you have any doubts till now? Doubts?
No, ma'am.
Okay, so that's all from my side today, and I have already announced that the quiz will be on Friday. So Friday from 5:30 we'll have the quiz, and it will be the format of the quiz would be similar. So it will be like 1 hour to 1 hour 15 minutes quiz you will have, and this time I'll try to give you shorter length, the length of the paper. I'm trying to give you a shorter one so that you will get sufficient time to solve all the problems. Okay, so yeah, so that's all from my side. If you don't have any doubts, then we can end today's class here, and we'll have tomorrow's class again at the scheduled time of 11 o'clock. Thank you, everyone.